Today I'm going to have an overall review on how to test the convergence of a given series. Based on my experience, here are the chronological orders of the things that you need to think about when you see a series. Right? So first of all, think about the divergence test, the test of divergence. If the limit of an is not 0, then sigma an is divergent. And you think about this one if you see that the limit is easy to compute. Sometimes although the limit is not easy to compute, but you have to try to compute them because all of the later tests that you try fail to work. As I said, if the limit is not 0, then the series is divergent. However, if you test and you see that the limit is 0, don't say convergence, right? Now, in the case that you get the limit equal to 0, meaning you still have a chance of convergence, but still have a chance of divergence. So at that time, most often you need to think about the ratio test and the root test, right? So if you see the factorial, then very likely that ratio test is going to be what you need. But if you see so many power n's, at that time the root test will be helpful, because when you take the root, the nth root, that will cancel some power n for you. Alright, now when you use ratio test and root test, you will have to compute some types of limits, and based on the result of the limit, you are going to say something about the series. If the limit is greater than 1, divergence. If the limit is less than 1, convergence. If the limit is equal to 1, inconclusive. And in that case, don't try the other. Meaning if you have tried ratio test and the limit was 1, don't try the root test. And if the root test gave the limit equals 1, don't try the ratio test, because if one of them gives you limit 1, the other will be giving you 1 as well. Now 3, if the ratio test and the root test doesn't work, then you can try the other test, but based on the type of the series that you were given. If it were alternating series, right, think about the alternating series test. Now, if the series that you were given is not an alternating series, then you can look and see if the terms are all positive. So if you have all positive terms, then you can think about comparison test, limit comparison test, and the integral test in the following order. Right. So first of all, I suggest you to use integral test. If the function f of x is easy to integrate, right? If the integration of f is not easy, you can try limit comparison test. If the limit comparison test is not easy to deal with, think about comparison test. Most often, if comparison test works, limit comparison test will work as well. So that's why I suggest limit comparison test before comparison test. If you are given a series that is neither alternatingly changing sign or all positive terms, then you can think about considering the series with the absolute value, so that you can turn every term into positive and use 4. Right. Remember, if the series with the absolute value sign is convergent, then the series with the absolute value sign, which is the given one, is also convergent. Sometimes you will need to split the series into simpler pieces. If you keep it the whole, then you wouldn't be able to use any test to confirm the convergence of this one. So at that time, you may think about how to split this one into simpler pieces. And for each piece here, you can try the above suggestions. Now, in order to be able to use the strategy here, there are two basic series that you will have to remember. So first of all, the sigma 1 over n to the p, this one is going to be convergent if p is greater than 1, and divergent if p is less than or equal to 1. The p-test. And the other one is the geometric series. This is very important, very, very important. For this one, you are going to have convergence if q is in between -1 and 1. And you are going to have divergence series if the absolute value of q is greater than or equal to 1. Now, in the case of convergence, this one is called the geometric series. Moreover, when the size of q is less than 1, sigma of q to the n, with n start from some capital N to infinity, is going to be equals to q to the capital N over 1 minus q. Alright, so first example. So don't try any test right away, right? Always try to pay a little bit attention onto the general term. The general term an is n minus 1 and 2n plus 1. And you can compute the limit of the general term easily, right? N is going to be very big. So this is like the limit of n over 2n. And then you get 1/2. 1/2 is not 0. So you can say that the series is divergent. Right? So you see that if you test the general term right away, it's very simple to compute, and you get the divergence almost instantly. Right, so note here. If the limit of the general term were equal to 0, it does not mean that sigma an is convergent, right? So that's the first example, very simple. Now let's consider the second example. Sigma 2 to the n over n factorial, right? Now if you look at the general term, it's of course 2 to the n over n factorial. So if you write it, it's going to be, now except the first one is going to be 2 and the second one is going to be 1, the later ones are always less than 1. And the more you go, the smaller the fraction is going to be, right? So smaller over time. So that means when n is big enough, the top is nothing compared to the bottom. And so this is going to give you the limit of an is going to be 0, right? Now, with the note that we had before, we know that when the limit is 0, it doesn't mean that the series is going to be convergent, right? That's something wrong to say. So, the divergent test won't help here, right? Then that time we are going to think about either ratio test or root test. Now, because you have the factorial, so very likely ratio test is going to be more helpful. So if you think about ratio test, you will have to first compute an plus 1. because an is this formula. So when you replace n by n plus 1, you do that for every single place you see the n here. So 2. Alright, so this implies the fact that if you compute an plus 1 over an, it's going to be this and flip multiply the an, right? By means flip multiply. Flip multiply, so n factorial 2 to the n. Now in the ratio test and the root test, you will have to put the absolute value sign. Now when you try to simplify 2 to the n plus 1 and 2 to the n, something cancelled here and you get 2. So this and this get cancelled. This is n factorial. N plus 1 factorial is actually n factorial. Then multiply n plus 1. And the n factorial will get cancelled and you get 2 over n plus 1. If you take the limit of this one, this is going to be the limit as n goes to infinity of 2 to the n plus 1. And of course that's 0. So in ratio test, you get the limit. You compare the limit with the number 1. And 0 is of course less than 1. So the given series is convergent by ratio test. Example number 3. Alright, so if you take the limit of the general term, you are going to get 0, right? So you cannot confirm anything. And you have to think about the other test, right? Here you see the negative 1 to the n, and you know that this is going to generate the plus or the minus and make the series being alternatingly changing sign. So we think about alternating series test, right? So for the alternating series test, we are not going to consider the whole thing here, which is an. We will only consider the ones after we filter out the sign. So this is bn. Alright, so you can see that your bn positive. Well, it's actually decreasing because the power 4 increase faster than the power 3. And then you have the limit of bn is 0. So you get bn positive, bn decreasing, and the limit of bn is 0. All three conditions hold. So the series is convergent by the alternating series test. Alright. Next, example number 4. For this one, you can see right away that the term is positive, right? Of course, the limit of the general term is going to be 0 because the top is always 1 while the bottom is increasing without bound. So we can try to think about ratio test and root test. Ratio test is not going to be helpful much because you don't see the factorial. Root test, that can be annoying. If you didn't have the ln, then you can take the root and that's going to be easy. But because you have the ln, that's not easy anymore. However, we know that if there is no ln, then this is a familiar series that we know the convergence for sure, because this is like 1 over 5 on to the power n, which is the geometric series with the q less than 1. So this is an, right? So all positive terms. So you can think about integral test, limit comparison test, and comparison test. The integral test is not going to be helpful because taking the integral of 5 to the x plus ln of x is going to be painful, right? We wouldn't want to do that. Limit comparison test, that's gonna work, but the fact is that here you can use comparison test and it's gonna be shorter. So an is 1 over 5 to the n plus ln of n. And obviously this is less than 1 over 5 to the n, which is 1/5 all to the power n, and this is the bn. Now sigma bn is convergent because is the geometric series with the q 1/2 absolute value is less than 1. Right? So it's convergence. So when you have an less than a convergence 1, it means that an is going to be itself convergence. Less than convergence implies convergence. Remember that. Is convergence by the comparison test. Now example number 5. So this is the general term. You can rewrite it as n over e to the n squared. Right, if you take the limit, of course, the exponential function here is much bigger than the variable itself. So the limit of the general term is going to be 0. You have to use other tests, right? So I just emphasize this from times to times to help you avoid the common mistake. Well, let's think what we can use here. We see the power n. Root test is going to help. So try root test. For the root test, we take the nth root of the absolute value of an. So you have the nth root of n over e to the n squared. And this is like the nth root of the n. And when you take the nth root of this one, it's like e to the n squared. The nth root is like the power 1 over n. And so when you simplify, you have e to the n. Now when you take the limit of this one, the limit of the nth root of n is going to give you 1. The limit of this one, as n goes to infinity, is going to be like infinity. So this is going to be 0, right? I put this in parentheses because writing 1 divided by infinity is not a proper way of writing. Alright, so you get 0. For the ratio test and the root test, you compare the result with the number 1, and this is less than 1. So you have convergence by root test. You can try the integral test as well because this is a series with all positive terms. So for integral test, you are going to test the corresponding infinite integral from 1 to infinity of the function here. So this is going to be x e to the x squared dx. And so you can make a change of variable, a substitution here. Right, so at that time you get du equals 2x dx. And that implies that x dx can be replaced by 1/2 du. And so you can replace them here. So x dx replaced by 1/2 du. This is going to give you 1 on the top and e to the u. Right, e to the u. Of course, this is going to be 1/2. If you take the antiderivative of this one, it's going to be this. Now you want to plug in some value for u, right? So we know that we forgot this. When x is 1, the square of 1 is 1. When x is infinity, you square infinity, you get infinity. So still 1 to infinity, right? So 1 to infinity. Now the fact is that if you do everything and write everything in a proper way, you have to write this equals to the limit as capital T goes to infinity of the integral from 1 to the capital T. Solve the integral from 1 to the capital T and then take the limit of t goes to infinity. That's the proper way, but I'm cheating a little bit here to save our time. The fact is that this function is very simple, so do the cheating thing is not going to hurt us, right? But for more complicated functions, when you have integral by parts, sometimes that's gonna hurt. So you plug in infinity here, you have e to the negative infinity, and you know that that's going to be like 0. So 0 here. And then you minus, with minus, you end up having plus e to the negative 1 and 1/2, so 1 over 2e. So this is a real value. The integral equals to the real value. That means that the integral is convergent. But the convergence of the integral also confirms the convergence of the given series by the integral test. So the series, the corresponding series, is also convergent by the integral test. So you have seen that not only one way is going to work, you can have different strategies to prove that something is convergence or divergence. Now next, example number 6. If you look at the general term on the top, that's the square root of n cubed. Down the bottom, you have n cubed without square root. So in the long run, the top is going to be much smaller than the bottom. So this is going to have the limit equals to 0. So you cannot use the divergence test again. Just try to emphasize that. Right, so we know that the divergence test is not going to have. If you use ratio test and root test for this one, computing the ratio or computing the root, the limit is going to be hard to compute, taking time. I'm not going to say it's hard, but it's going to take a lot of time. So we are not going to use ratio test because actually we don't have any factorial here. So ratio test is not very powerful when you don't have factorial. And you don't have any power n here. So actually root test is not going to help at all. And so we are going to think this is not an alternating series. So alternating series test is not going to help. But this is going to be series with all positive terms. So either we can use integral test, comparison test, or limit comparison test. Now look at this function. If you take the integral, I don't want to do that because that's going to be hard. So we can either use limit comparison test or comparison test. The way we are going to do is, first we think about this one and try to figure out what is the most familiar, the closest order series that you know the convergence or divergence. Of course, you try to make it like the P series or the geometric series. In this case, trying to make it the P series is very simple. Let me show you the way I'm going to figure out what is the Bn that I'm going to use. So this is An. Now when n is huge, An, which is this one, would be similar to, right? Because when n is so huge, the number 1, the number 2 will not contribute much. This is going to be huge, but compared to the cubic here, it is nothing, right? So you can ignore it as well, and eventually this is going to be like the Bn that you may want. If you simplify it, you will get 1/3 of 1 over n 3/2. So you are going to compare An and Bn, which is the one that you are familiar with, and take the limit as n goes to infinity. Now if you do this, is the limit. An, when you divide Bn, it's actually flip multiply this one. Now you combine them. So this is like you are going to have the square root of n cubed plus 1. This division by 2 on the exponent of the n is like the square root, right? So that's gonna be combined here. So you have square root of n cubed. So that's gonna be like n cubed here. And we are going to keep the number 3 outside. and then you have 3n cubed plus 4n squared plus 2. So this is like you are going to have the limit 3 times the square root of, you distribute, you get n to the 6 plus n cubed. Now when n goes to infinity, this is nothing, this is nothing, this is nothing compared to the biggest one on the top and the biggest one down the bottom. So this is going to give you limit 3 times the square root of n to the 6 over 3 times n cubed, which turns out to be, so you can cancel the number 3 and you get the limit of the root of n to the 6 n cubed. This is going to be 1. This is a real value in between 0 to infinity. Right. So by the limit comparison test, the convergence and divergence of an will be the same as the convergence and divergence of bn. Right. We know that sigma bn is 1/3 of sigma of, right, this is bn, so that's going to be 1/3, and you can pull 1/3 out of the sum, is convergent by the p-test. In this case, p is 3/2 greater than 1. So that implies the convergence of an as well. And what is an? We may want to rewrite it one more time. Is convergent by the limit comparison test. Next example. Example number 7. Well, this is the case when I say that you will have to split the general term into smaller pieces. This is the same as the sum of and simplified. So you know that this is going to be the difference of the two familiar series that you know. One is sigma 1 over n squared, which is the p series, and one is sigma of 1 over 2 to the n, which is a geometric series with q equals 1/2, less than 1. Alright, so we know that sigma 1 over n squared is convergent by the p-test with p equals 2 greater than 1. And sigma of 1 over 2 to the n, which is the same as sigma of 1/2 on to the n, is convergent because of the geometric series, right? Geometric series with q equals 1/2 less than 1. So this implies that 2 to the n minus n squared over n squared 2 to the n is going to be the difference of the two convergence series. A convergence 1 minus a convergence 1. So that is going to be convergence.